Hi everyone. I'm Rish. I'm the second year PhD student on the Duck team in Esperance-Clay. I'm advised by Frederic. And today I'll talk about Lean4Less, which is basically a kind of model made to Lean4Lean that applies
don't worry, it's coming back.
dispatching to Lean terms so that they no longer rely on proof relevance to type. And it's still very much a work in progress, so you can also take this talk as a request for comments and suggestions. So I'm sure the vast majority of us know about Lean. So it's a proof system developed originally by Microsoft and more recently by the Lean FRO. And this type theory is very similar to that of Coq, based on the calculus of inductive constructions within predicative universes. And it has a very large and quickly growing mathematics library called MathLib. It's import graph, so it's very big and it's growing quite quickly. So yeah, that's Lean. And so what we want to translate. So some reasons why we'd like to translate between proof systems is to make, so specifically with respect to Lean, is that Lean has a lot of formalizations, so we'd like to make all those formalizations available to other proof assistants. And we'd like to improve our confidence in Lean's proof libraries by being able to port those proofs to other proof assistants and checking that they are able to type check. And lastly, we'd like to prevent duplication of work in writing libraries for mathematics and programming between proof assistants. So the idea with the logical framework of Deducti is basically, rather than taking the naive approach of doing a pairwise translation between each proof assistant, we ideally like to go through a central kind of center point, which can take the form of a logical framework. And in this logical framework, we can represent different theories, and we can hopefully economize more efficiently the similarities between the translation of these theories within the logical framework. And yeah, so we translate through this central logical framework. So Deducti is one such logical framework that's specifically designed with translation in mind. And its type system is a lambda pi calculus modulo rules. And its definitional equality is based on normal forms following bit reduction and application of Riemann rules. So translation to Deducti and from Deducti follows generally these three steps. You first translate from your initial theory A into Deducti's encoding of A, so we can call it dk mod A. And we then translate from dk mod A to another compatible theory B that's also been encoded in Deducti, which we can call dk mod B. And lastly, we want to take those dk mod B proofs and output them to the target system, B. So we translate from dk mod B back into B. So a little bit on Lean's type theory. Lean has a type theory that's we can call the algorithmic type theory. And it's fairly standard. And here we can see there's a universe hierarchy. And this is where impredicativity comes into play, where we use where we can basically we can determine which universe the output type of 4Ls are based on whether or not the output type is in prop. And there's also the conversion rule. And these are the definitional equality rules. So these, in particular to note here, are the head reduction relation, which covers beta and recursive reduction. And we also have a conversion rule that basically lets you type a term. So you can type a term as any type that is definitely equal to. And also you'll note the proof relevance rule. So whenever you have two proofs of a proposition, we make them definitionally equal, which implies that they will be equivalent for the purpose of typing. And I should mention that these rules are a little bit outdated since Mario's recent Lean4Lean paper. He actually combined these into like an all-in-one judgment. So the typing and definitional equality are kind of merged together. But yeah, this is the formulation from his master's thesis. So yeah, so in Lean we can also define inductive types that are what are going to be generating our recursors and recursor reduction rules that we include in our definitional equality judgment, or that head reduction relation. So this is, for example, the natural number inductive type. And you can see here we have zero and successor, and it generates this nat.rec recursor function. And we can use this recursor function to, for example, define the decrement function. And we can see over here that based on the fact that we can apply reflexivity to prove that these sides are equal, we know that Lean is treating them as being definitionally equal. And that's due to the rule that Lean has for reducing this recursor. And we also have some more complex inductive types, and like, for example, ACK, which is used for defining well-founded relations. And we can see here that these inductive types can have recursors that are, can have constructors that are recursive, and that they can take arguments that are like functions that output the same type that we're currently defining. And those gives us slightly more complex real rules with inductive hypotheses. So to translate from Lean to Deducti, our base translation will be interpreting Lean as what's called a pure type system. And anything that's outside of that base translation we'll have to handle specially. We'll need to think of a way to encode any additional rules as rewrite rules, such that these rewrite rules that we make for all these additional equalities, they must form a complement system. So every term must have a unique normal form. So if you rewrite and the form of any term diverges at any point, then we must know that they will eventually converge again. Any two, so obviously we want to have any two terms that are definitionally equal in Lean to have the same normal form following rewriting and beta reduction. And rewriting is a bit limited in that it's based solely on syntax matching. So many of Lean's rules are not that simple. And for example, if we want to encode Lean's natural numbers in Deducti, we have so first of all, this is the machinery of the PTS pure type system encoding. So this is how we define like our universes and how we are able to define types in Deducti without needing a full universe hierarchy. So basically, this is our natural number type constructor and the two data constructors, 0 and sec. And this is the recursor rule type. And after we declare the type of this recursor rule, we then declare a rewrite rule for that recursor. So now let's talk about the proof relevance rule. So this is one that's a bit more tricky to encode as a rewrite rule. So it's not obviously any kind of reduction rule. So we've got to think of a way to have some rewrite system such that any two proofs of the same proposition type have the same normal form. And so our first idea may be to kind of like erase proofs. So for example, here's a definition that uses proof relevance in order to type. So we have this this like proof indexed type, and we have this example definition, and it's able to type something that has the type TP as TQ based on the fact that P and Q are the same proposition, proofs of the same proposition. And we can think about encoding this in Deducti with this erasure symbol. And basically what it does is it, given a proposition and a proof, it will just rewrite to erase the proposition. and then, sorry, a rewrite to erase the proof. And then we have basically a kind of a normal form, because if we just only care about the proposition and not the proof, then we've accounted for our proof of relevance in that way. So this could be a viable idea, but it's not as simple as it looks. So first of all, it runs into typing and pattern matching issues in deductee. So basically, yeah, so this is a bit complicated to explain, but we would probably need to extend deductee in a few ways that may be okay, but it's not immediately doable. So yeah, that's an issue that we run into. So yeah, this is something we may be able to get around, but I think that a real issue that we run into is later on with this property that Lean has of k-like reduction. So here, if we have, basically, we have Lean has this has some support for like k-like types, in that they behave kind of like equality, the equality type, and that they respect the axiom of k. So what that means is that if you have an inductive type that has one recursor, one constructor that does not carry any data with it, so any arguments that it has must appear in its output type. If you have that, then it's treated as its recursor is allowed to operate in the same way that the equality recursor can operate under axiom k. So what that means is that in this example, we have something of this k type. And its type here, it matches the type that we'd expect from its constructor. So therefore, we're able to rewrite this recursor without needing an explicit constructor as the major premise here. We can just rewrite it immediately with just this variable. But in this example, this one actually does not work, because this type over here uses 1 instead of 0, so it doesn't match our expected type here. So this one would not work in Lean. So in this case, this happens to be simple enough for a rewrite rule. So basically, we can kind of encode our typing requirements on this proposition H. We can encode those requirements as a syntactic requirement in the rewrite rule. So here I've made the rewrite rule such that it requires a 0 in this next position. So if we have that, then we know that we've handled all the cases we need to, because we just have this case. So this is it. This is enough to handle the k-like reduction for this particular inductive type. But in general, this is not really possible, because instead of 0, we may have had some arbitrarily complex expression that depends on A and B when we defined our constructor here. And then if we have a complex expression, or even just A plus B, that's already very complicated for us to match on in a recursor, in a rewrite rule, because we need to match that syntactically. And it's not really clear how to do that, because A plus B is also defined in terms of recursor, and when we expand that, then it would be very complex to match on syntactically in deductive. So yeah, so there are limits to this approach that we need to get around. So yeah, so for this example again, we already talked about this. So yeah, for this to be correctly typed, Lean has to apply proof relevance to say that p and little q are definitionally equal. So this is something that we can't directly translate into deductee, because deductee obviously doesn't have proof relevance. So however, we can kind of get around it by patching this term with a proof relevance axiom and typecasting to get around it. So here we can add this proof relevance axiom. So as you'd expect, it takes given any proposition and two proofs of that proposition, it gives you a propositional equality of those two proofs. And here is the congruence argument principle. So yeah, we know what that is. And we have also casting, or otherwise known as transports, which lets you basically, when you apply this to a term, with some type A. If you have proof that A is equal to type B propositionally, then that application of that cast will be typed under B. So yeah, we can use this to basically patch this expression T that we had over here with a cast together with an equality proof of the fact that TP is equal to TQ using our proof relevance axiom. So the question now becomes, can we do this kind of patching in general? And I think the answer is yes. So our goal is to translate our terms into some theory, which we can call Lean-minus, where our proof relevance rule has been replaced by a proof relevance axiom instead. And so yeah, I just use this notation for our new type system. And yeah, so this is the propositional equality type. And so this is a proof this is something that's obviously provable in Lean proper by just applying reflection because we have proof relevance. So in fact, Lean minus is a strict subset of Lean. So now we can, so now since we've lost a bit of power in our theory, we can maybe think of trying to recover things. So we can think about this reflection.
Sorry, I missed the point. It's very stupid. So there was an helicopter. Yeah. So you said Lean minus is what is exactly Lean minus compared to Lean, and why is it included? Sorry.
Lean minus is the same as Lean, except we've removed proof relevance. So Lean had a proof relevance rule that we've removed.
Okay, so you replaced proof relevance by,
the axiom.
Well, you could also prove relevance, but it is a little bit weaker. That's what you claim, yes?
Yeah, it's weaker. Yeah, because it's only an axiom, it's not an actual rule of the theory itself.
Okay. Thanks.
Okay, yeah, so yeah, we can think about this reflection rule from extensional type theory. And this rule, what it does is it basically, given a propositional equality between any two terms, it lets you have a definitional equality between those two terms. So we can extend our Lean minus theory with this extensional rule, and now we can recover our proof relevance simply by just plugging in our proof relevance axiom for this proof that we need of the propositional equality. So therefore, we know that any Lean derivation, typing derivation, can be translated into one in Lean minus E by just replacing all our uses of proof relevance by this. So now Lean itself is actually a strict subset of this Lean minus with extensionality.
Lean minus with extensionality is the same as Lean with extensionality, right?
Yes. Yeah, so to summarize all our theories, we have Lean minus with proof relevance, but not as an axiom, but not as a rule, and then Lean with proper proof relevance definitional equality rule, and then Lean minus E with proof relevance as an axiom, and the reflection rule of extensional type theory. So you can see that we can easily translate from Lean to Lean minus extensional. So in order to go to Lean minus now, it's sufficient to translate from Lean minus extensional to Lean minus. And so this is exactly the task of translating from extensional type theory to intentional type theory by eliminating the reflection principle. Reflection rule, sorry. Yeah, so this is a solved problem, and an algorithm for this was described by Winterhalter and others, and it was actually formalized in Coq in this repository. So yes, so at first glance, this may seem like more work if we want to translate from a fully extensional theory to Lean minus rather than from just Lean to Lean minus. But in fact, I have a strong suspicion that it's necessary because the proofs in Lean can really appear anywhere in terms, and in particular within types. And translations, we can see with this example, they can already get quite complex when that happens. So in this example, basically we have a proof-indexed proposition, and we have two proofs of that proposition, of this proposition P, and we have proofs of this applied to different proofs. So now these things are definitionally equal in Lean, thanks to the proof of relevance principle applied twice. So once to equate these types, and then once we have an inequality between these two proof types, then we have definitional equality between these. So it's like a nested proof of relevance case. And yeah, so in this case, if we wanted to prove something like this with a term of like this type, which uses both P and QP, we would need if we were in Lean itself, we could just type something as T P QP as T Q QQ quite easily just by using T itself. But now it gets quite complex because we have that nested proof relevance. So now we need to, so you can see it's quite complex. And in fact, we need to bring in this heterogeneous equality type. We need to use this instead of our normal equality type because in Lean minus, these types are only propositionally equal. So if we want to apply our proof relevance rule, it also needs to have proof that those propositions are equal, and it needs to also give us a heterogeneous equality proof. So so it gets quite complex. So this is why I have a suspicion that this is actually quite a complex translation to do.
In this, you changed the definition of proof of relevance for this, but then it should be equivalent, right? To the first proof of relevance axiom that you had. This one is heterogeneous.
Yeah, that's the only difference, is that it's heterogeneous.
Okay, but this could be a theorem proved from the first proof of relevance.
In Lean, I don't think you could prove this.
Well, using the proof of relevance axiom, but not using it like in Lean minus with the proof of relevance axiom, you should be able to prove this version of proof of relevance.
Oh, good question. I think you can't really. Oh yes, I think you're right. So that's a very good point. I can maybe do that. Yes. So yeah, thank you for that. Okay. Yes. Okay. So so using this directly, so you're trying to use the Coq formalization of this directly may be a bit difficult because the input that we need to our this tool will be from a minimal extensional theory that was used in the paper, and we'll need to translate Lean derivations to this minimal theory. And again, like any definition equality that Lean uses, will need to be like somehow temporarily substituted with like axioms, similarly to how we would do for proof relevance. With axioms plus the reflection rule. And we'll need to get these derivations in the first place, and there's currently no way to do that. So we'll need to modify some Lean type checker to give us a derivation. And the output of this tool will also be terms from a minimal intentional theory, and we'll have to translate those terms back into Lean, and we'll have to go back and undo all of our uses of these temporary axioms to get a good Lean term. So consequently, and also so this will also not be optimized at all. So the output will be very large, and we'll have many unnecessary casts and redundant proof terms. So we'll need to do some post-processing to pare it down and get something kind of minimal. So what I decided to do was instead to modify the type checker to like patch our terms as necessary in parallel to type checking. And in doing this, I also hope that we can get a really minimal translation by only applying these casts and proofs where we actually strictly need them in order to have a well-typed term. So one promising implementation for this, for us to modify, is Lean4Lean. which is a recent port of Lean C++ checker code to Lean4, which is kind of going in the direction of Metacoq. And the functions in this implementation that are of primary interest to us are these in the main type file versus the type inference function. And then we have the definitional equality checking function. And we also have a function that gives us the weak head normal form for an expression. So we will basically modify these functions to return an additional optional expression that will be sum if we needed to apply our proof relevance axiom at some point to get these properties. So in the infer type case, it will output the patched version of our input expression that we were trying to infer the type of. In the definitional equality case, it will give us a proof of heterogeneous equality between the left and right hand sides that we passed in. And in the weak head normal form case, it will give us a heterogeneous equality between our input term and its weak head normal form. So yeah, so in infer type, these terms will be cast as necessary, and we'll inject these casts in order to basically they'll be using our proofs that are given by is the EQ and weak head normal form to as the proof argument to that cast. And so there are a few cases where this occurs. The first is when we check that when we have a defined constant in Lean, we need to check that its declared type is equal to its actual infer type of the value that we gave it. And in the application case where we apply some function, we have an expected type on the inputs. So we will need to potentially apply casting to its arguments that we after we infer its type. And in the let case, similar to the definition case, we also in Lean we also annotate those with expected types. So we would also potentially need to do some casting on the value. And also in Lean there are places where we expect certain head constructors after calling weak head normal form. So for example, when we have lambda and for all binders, we expect the types of their domain arguments to be sorts. So we expect sort expressions. So we may also have to cast those to actually be in sorts if it's necessary. So the modified definitional equality and weak head normal form routines will give us heterogeneous equality proofs. And this is, I'll reiterate, this is necessary because these left and right hand side types may only be propositionally equal in Lean minus. And we'll need these lemmas in our translation. So we'll need the heterogeneous equality. We'll need proof relevance for heterogeneous equality. And we'll need some congruence lemmas for our application lambda and for all cases. Yes?
One of the reasons why heterogeneous equality has been sort of such a difficult tool to use in Lean has been exactly because this application congruence rule sort of doesn't hold the way we want it to, and because of that you can't just pretend that heterogeneous equality is all you have and work in some kind of untyped set theory kind of situation. So exactly how is it that you managed to circumvent this issue and get something that worked?
Yeah, so I did prove this lemma. I did run into some challenges along the lines of what you mentioned, and you'll notice I have this kind of complicated HUV hypothesis, and this is really the most complex part about this, because when I in my implementation I actually need to call the for all or the for all case like as a subroutine to be able to populate this hypothesis. So it's really not very efficient, but maybe it's the best we can do. I don't know, but yeah. So yeah, with all these hypotheses, you can actually prove this, and it uses also function extensionality and K-like reduction in its proof. So yes, so this is our testing plan for Lean. I think I'll call it Lean4Less, but I'm still open to suggestions on the naming. And we'll test it on Mathlib 4. And so the kind of flow here is that Mathlib 4 will have some Lean files and inputs to Lean. Lean will output some Olean files, and these Olean files will represent an environment. And this environment we can pass as input to Lean4Less. And Lean4Less will then output our patched environment that uses our proof of relevance axiom and our congruence lemmas, among some other things possibly. And we'll also, for verification purposes, output a special environment that is the original environment, but with equality proofs added between all of the original and patched types of all the constants we had in the original environments. And these are verification steps. So we'll first type check our patched environment with a modified kernel representing Lean minus. So basically, this is just going to be Lean for Lean with the proof of relevance routine removed. And we will take our verification environment ET, and we'll type check this with the original kernel. And basically, what this will do is that we'll make sure that we, for example, didn't just write everything to have the type true. So we'll make sure that the meaning of the types that we translated were not changed as a result of translation. And then, yeah, of course, the actual output, output of our Lean4Less will be this environment, which we'll be able to use in external tools like translators. So there are also some prospects for this implementation. So this patching framework should be pretty much consistent with what was described in the general ETT to ITT translation. So it should be possible to extend it, firstly, to handle basically any other definitional equality in Lean, KLF reduction, even recursor rules and beta equivalence, though we probably don't want to go that far. And this could also include new user-defined definitional equalities. So we know that ETT itself is undecidable, but we can maybe add some kind of partial extensionality to Lean via some mechanism that we provide to the user for registering new and deriving new definitional equalities in Lean, or like a limited subset of Lean's propositional equalities. So we could think about this new theory Lean extensional star that basically has a kind of qualified reflection rule that uses some routine. I have no idea what this could be, but some routine that is able to compute equality proofs for use in this extensionality rule. And yeah, we could use Lean4Less to translate from this extensional version of Lean back into Lean. And then we could make it even more interactive and think about maybe integrating this somehow with Lean's elaborator and allowing you to reason live in Lean with this set of defined definitional equalities in Lean. And so that could be useful for mathematicians. So my progress so far, you've kind of caught me at a very, I'm very much at the cusp of having some interesting output. The core implementation is pretty much done, I think. Well, there are probably bugs, but I'll need to work this out. So I already have some output. I can see, in text form, I can see some translations of terms that have patching applied to them. But I need to still figure out how to do the Olean stuff, so Mario can maybe help me with that. I'll need to do that for all the user and standard library modules as they're patched. And obviously, I'll probably run into bugs and runtime errors. And also in the output itself, there may be some syntax and typing errors that I'll need to work out. So yeah, once we can patch and type check Mathlib with Lean4Lean minus proof relevance, we can try to push its limits by eliminating more commonly used definitional equalities like recursor reduction, beta reduction, and delta reduction, and to help us identify any trickier bugs and have more confidence in the translation as a whole. So, yep.